Hello everyone, this is Stuart from Newtons4th and I'm going to do a video just showing you setup advice or recommendations when you're working with a motor drive system, a variable speed motor drive. Anyone watching this video would be best to have seen a quick walk around I did in a separate video just showing what I'm connecting to, which is a 2-motor, 2-inverter, back-to-back drive system where we can load one motor with the other, look at torque and speed and various drive and load conditions. But for the purpose of this test, I'm just going to look at one of the motor outputs to talk about frequency detection. I happen to have at the bottom here a PPA5500 that I was using because I can do 3-phase in, 3-phase out on this device, and I was doing some work with that. Whereas with the 5500, it's a higher performance instrument, so it's got wider bandwidth, higher sampling rate, wider dynamic range, but it will be perfectly suitable for 6-phase applications or even more by using multiple units going into our software, which will take data real time. And since asynchronous applications should have asynchronous measurement, then that's a very appropriate way of using them. So even when we're using the PPA35 and the instruments working together, one side of the instrument connected to one motor is asynchronous from the other side, which is connected to a different motor, which will be at a different speed, and you should always measure asynchronously. We have a white paper on this on our website. The white paper number is 120, and that's worthwhile reading because there's a lot of misinformed information about the benefit of synchronizing anything or everything, and that isn't good for reasons we explain in that application note. Basically, only one frequency can be synchronized if you've got two, and therefore one will be good, one will be bad, and will probably modulate, or almost certainly modulate. Anyway, I've just powered up the instrument and it's just picking up a bit of noise, 50 Hertz here, and I'm going to switch on my drive. And what we see there is 1 kilohertz, and the reason we see that 1 kilohertz is that the default settings, which happen when the instrument powers up, it has factory default. The default settings are based on loads that we don't know, so we make some assumptions and we default to voltage phase 1 as the frequency, which is often okay, but we don't do other settings unless we specifically know we should. And the PPA series are very, very flexible, so there's a lot of settings and you have to know which ones to use to be able to get optimum measurements, and if you use them correctly you'll get exceptionally reliable and accurate results. So this 1 kilohertz, where does that come from? It's coming from the PWM waveform that if I zoom in a bit, we can see it's pulse width modulated, and it happens that the carrier is a kilohertz. So that's what we're seeing when we have the voltage detection. And that's quite natural because that voltage detection will find the edges. Now, if we go back into the scope, we can see that it's triggering off these edges because we're triggering off voltage. If I go into the scope mode and change from voltage to current, now we're going to be triggering off current. So when I go back, now we've got stable measurements. But I've done this not because I want to focus on oscilloscope measurements, because I don't. The reason the oscilloscopes can't measure power, totals and fundamentals anywhere near as accurately as a good power analyzer is because by virtue of them having fixed digital windows, they will pretty much never be synchronous. So it's pretty easy to see that if you've got a fixed window and I change the frequency, then the number of waveforms is going to be changing. The same is true if I just change the time base, just like an oscilloscope. If I change the time base, the number of cycles will change, but I will never have a whole number of cycles. And that is a problem, because if you do analysis of this with either an FFT or a DFT, then you're going to get error associated with the fact that you don't have a whole number of cycles in the waveform. So when you're making optimum power measurements, the frequency should always be your first thing to check, because when you've got that, the fundamental right, and that's the fundamental column there, and the total is there, that's wideband, then the ratio of those numbers is going to be correct. And we're getting some plausible looking numbers, and that's just because they approximate to the right value because it's averaging, okay? But there's a number of ways to do that. The easiest way and the most common way in a motor drive is to change from voltage reference to current reference. And when I do that, this isn't a kilohertz anymore, but it's still bouncing around a bit. And why is that? Well, that's because there's still noise, high frequency noise, superimposed on the current. So although it looks perfectly clean, there are noise components which we can see every now and then, and we'll see more and more. If we zoom in, you can start to see noise components. And they are what's making the frequency bounce around a little bit. So what you should do is go into the coupling menu and change the instrument from 2 meg, which in this application it simply doesn't need, to 200 kilohertz. Now this is a soft 200 kilohertz. It's 2 kilohertz 3 dB with 10 dB per decade fall off, so it's not a massively strong filter. And 200 kilohertz will include all the components that are going to be meaningful in most drives. So it happens also that that's wider than a lot of power analyzers' bandwidths anyway, so we call it low, but it's absolutely appropriate for this application. So if I come back and we've got current detection and a 200 kilohertz bandwidth, now we're detecting the frequency correctly. And when we're detecting the frequency correctly, we're going to get all the fundamental components correctly and all the totals. Now, we can go through phases, as you may be familiar, 1, 2, 3, sum, 1, 2, and 3. 1, 2, and 3 fundamentals, so we can look at either totals or fundamental components for all 3 phases, and then neutral, which is computed by instantaneous sample multiplication to calculate what the neutral would be, and then back to phase 1. But the key is we've got the frequency right. Now there are different circumstances where current may be okay, and it's generally speaking it's a good way to go. But we have something that helps even more, and that is a PWM mode. And the PWM mode has some filters that are much lower frequency, but significantly these frequencies, although they look very low, these are in parallel. This is a digital filter in parallel with the main input, so it does not filter the bandwidth of the instrument. The measurements won't actually change. All this will do is enable the PPA to reject noise more effectively, and the measurements I'm going to get now are the same measurements that we had before. Before it was 152 total and it was 162 fundamental. They're exactly the same, even though I've got that 4 kilohertz filter, or rather the one that started at 400s and I selected 250 hertz. And the reason I selected 250 is that's less than the carrier frequency but more than the total frequency I want, or the maximum frequency I want. And for that reason I'm getting rid of all the PWM noise as far as frequency detection is concerned, not bandwidth, okay? And this filter is so effective that we can overcome one of the problems with current detection, where if the current goes down, you lose the ability to find the frequency. If I go into this mode, I can even change it to voltage, which, if you remember, it couldn't make measurements at all. And even with voltage detection, we're going to be able to get some measurements. There we are, 25 hertz. Now I'm going to go back to current measurement. Just to show that the two values are the same. So 24.9. 24.9. So we're now detecting the frequency from that waveform without reducing the bandwidth. I've just gone back to power again, and that means I can wind the frequency up I can wind it down, and we start to see something else here, because I'm winding it up and down and it's tracking the frequency, but it's got filtering in it, so it's not as fast as I might like. So if I go into acquisition, what I can do is take smoothing out. So instead of having something that's smoothing, I can take the smoothing out. And something else you can do to make the tracking work better is go into acquisition again and go into advanced options. And in advanced options, it's got something called frequency lock. Now that's normal, but you can have normal, constant, where you fix a frequency that you want. Say you want to analyze something that says at exactly one frequency, you can set the frequency and lock onto it. Or you can set dynamic. And the reason for setting dynamic is that normal frequency detection will make a judgment about whether a fast change has been a loss of the frequency detection, and it will start sampling again. Whereas dynamic will allow you to track and it won't restart the sampling process. So now when I go up and down in frequency, you'll see it tracks faster. And I can show this even more if I change the speed from normal speed to fast. Now I've got no filtering, but as I go down and up in frequency, it's tracking it. Now, these situations or these settings aren't all universally best for all applications, because you may want to have some smoothing, in which case we can add some normal smoothing. And that will make measurements somewhat more stable. I may not want to go fast, because if you go too fast, low frequencies become more difficult to detect because the measurement's faster than the frequencies. And it's important to remember that every time we're making a measurement, it's a whole number of cycles and there's no gap. So you don't have to go fast to be able to see it, but you can track waveforms, or you can track the frequency, make measurements, zoom in and see data in more detail, or zoom out. And then there's a whole host of other settings that we can use in ranges. For example, we can have full auto range, or we can fix the range to stop the range changing. We can have range up only, so that it will range up as we power up, but it won't range down, so that we don't lose data when you have some hysteresis. So there's a number of settings, but in terms of frequency detection, the importance of frequency detection and the value of this in motor drive work, I hope it's been useful. Thank you very much indeed. Bye for now.